Now we want to take our newfound knowledge and apply it to some real-life context. So in the United States, the year each coin was minted is printed on the coin. To find the age of a coin, simply subtract the current year from the year printed on the coin. The ages of circulating pennies are right skewed, assuming the ages for circulating pennies have a mean of 12.2 years and a standard deviation of 9.9 years. And we're going to draw a random sample of size n equals 40 from the population. All right, just so everybody understands the idea here. This is the age of circulating pennies. Over here you have newer pennies, young pennies, fresh from the mint. And over here we have older pennies. And of course, over time, it's rare to find a penny that's significantly old that's in circulation. So that's key. These are circulating pennies. These aren't, pennies that you're hiding away in jars for years after year. This is in circulation. It's in the economy. Right? It's being used at restaurants and theaters and such. All right, so now let's have a little review of section 1.1 for a second. So we went over all these definitions way back in the day in section 1.1. All right, so what is the population? So what we're talking about is the ages of circulating pennies. So the population would be all circulating pennies. And just a reminder, it's not the age of the pennies. Age is what we're measuring about them, but the pennies themselves make up the population. And the sample is the random group of pennies. Technically, they're also circulating, but I'll just write random group of pennies. And the sample size, which is little n, is 40. Now, the age of a penny. So if you know the age of a penny is 20 years, is that value qualitative or quantitative? And the answer, of course, is that it's quantitative. We can actually do meaningful calculations. Age is a number that we can use to do meaningful calculations. There we go. All right, now some extra review. Let's talk about section 1.2. And of course, why are we putting these kind of questions in here? Well, because everything we do builds on itself, of course, but also there's eventually a final exam that's cumulative, right? And so you see how we can fold in those earlier ideas into these things. Okay, so let's look over the definition of these items. So cross-sectional studies are observational studies that collect information about individuals at a specific point in time. Case control studies are a little weird. They're retrospective. They require you to either look back in time or at existing records, and they generally match up people. I look at the records of people that have had heart attacks versus the people that have not had heart attacks, or I look at the records of smokers versus the records of non-smokers, that kind of thing. So we don't really have that here because we don't have pennies versus quarters. We just have pennies, right? So that's not quite going to work for us. Cohort is when you identify a group that you're interested in, say pennies, and then you say, okay, starting from this point forward, I'm going to track them for the next 20 years, right? But you have to actually do that tracking over a long period of time. All right, so let me just kind of quickly write those in, right? So this one is the snapshot in time, right? So this is looking at pennies right now. Right? It's a snapshot. This one is looking at the records of pennies. If we had such a thing. Like pennies versus nickels or quarters or something like that. And this would be starting now, we want to track pennies. Well, it doesn't have to be start right now, but we want to track pennies for a considerable length of time and see how they do in the world. And I think it's pretty obvious which one we have here. We have a cross-sectional. We're just saying, hey, what's the age of pennies right now, Right now, it's this. Right? We're not looking at pennies versus quarters. We're not saying, hey, I'm going to start tracking pennies from this point forward. We're not doing any of those things. So therefore, it's got to be a cross-sectional snapshot. Lovely. All right, so now let's get back to Chapter 8. Let's verify the conditions of the central limit theorem for the mean are met. Okay, well, that's back a couple pages, but the central limit theorem is the big gray box, right? It's also in your yellow packet for your notes. Oh, it might not be yellow, depending on what semester you're watching this, but your exam notes packet. All right, so the conditions are random, independent, normal. Random is almost always given somewhere. So let me write this down. Random, independent, and normal. Okay, so random is real easy because it says right here that it's a random sample. So you can say, yes, it's given. Right? Given means it's literally written in the problem that it is random. Lovely. All right, now independent. Well, it's going to be a yes, but I'm going to have to prove it. All right, so to be independent meant you need little n to be less than 0.05 capital N. Now here's the trick. We don't know what capital N is. It was never given to us. At nowhere in this problem did I say, hey, there's 54 million pennies in the world. All right, since I didn't give you a number, then you can't use a number. So you're going to have to just write what it is. So we said it was all circulating pennies, right? That's the population. This is just the population size. So it's how many there are circulating pennies there are. So we'll just say all circulating pennies. We will do this a lot, right? A lot of the times we don't know the population size, but we know it must be huge. I mean, there's got to be tons of circulating pennies. So this is, of course it is, right? By logic, it must be. So we're kind of waving our hands at it a little bit like a magician, right? We don't know what capital N is, but we know it must be a really big number because it's all the circulating pennies there are in the US, which is a huge amount. Therefore, 40 is considerably less than 0.05 of all of those pennies. But you have to write this, right? You can't just say capital N. You have to kind of write what capital N is in words. Here, I'll make a note. Either you're given capital N, right? If you're given capital N, use it, right? If N is not given, then write, then, that's an N, write in context for the population. That's key, right? We will do that a lot because we are very often not given the population size. Independence is the weirdest one, but you get used to it because you do it a lot. But normal, we have to pay attention to. Normal is right here. We need N to be bigger than or equal to 30. Okay. Well, or we need to know that it was, the distribution was normal to begin with. But we actually know that it's not. We know that it's skewed right. So we can't, just say, oh, it's normal. Given. It's not given. So we have to prove it. And the way we prove it is by having little n, which is our sample size, be bigger than or equal to 30. And there we go. So we have this bit, we have this bit, and we have this bit. Random, independent, normal are given that explanation, and then 40 is bigger than 30. Therefore, the shape is normal. We just proved it. The center. Okay, well, and the spread. Again, back to that central limit theorem, because that's what we're working with. The center is the mean, which was the mean of the x bars, the mean of the means, which was 12.2 years. The standard deviation of the sampling distribution of sample means is called the standard error. Right? So it's sigma with an x bar. You can write it this way or this way. You don't have to write it both ways. It's sigma over the square root of n. And by the way, when I say symbols here, those are what I'm talking about, right? or this one, either one. And then I don't know why I said explanations, because it's not really explanations. It's really the formulas, right? The formula's right here. So that would be 9.9 over the square root of n. N was 40. So I would go put that into Desmos. Okay. Oops. If I can get my papers away from my keyboard. 9.9 divided by square root 40. 1.5653. There we go. .5653. This is also years, by the way.